Hi, I'm Daniel Kasenberg, and in this talk I'm discussing my work with Ravenna, Thielstrom, and Matthias Scheutz at the Tufts University Human-Robot Interaction Lab on generating explanations for temporal logic planner decisions. At the HRI lab, one of our long-term goals is to develop artificial agents which can learn interpretable objectives both from language and from behavior, can behave competently with respect to these objectives even when they conflict, and can explain their behaviors to human teammates in terms of these objectives and correct either their objectives or their world models as needed, all while operating in the same environments, namely Markov decision processes, in which reinforcement learning agents have been successfully deployed. We're going to assume an agent operating in a Markov decision process, or MDP, which consists of a finite set of states, a finite set of actions, a probabilistic transition function, an initial state, a discount factor, and in our case, a labeling function which maps each MDP state S to a set of atomic propositions true at S. Our explanation approach will assume a deterministic environment. Our running example will be the ShopWorld domain, a simple MDP in which the agent is a robot sent to go shopping for its user in a store that sells a watch. The user wants the watch, but gives the robot insufficient money. We're representing agent specifications in linear temporal logic, or LTL. For those unfamiliar with LTL, it is a simple propositional logic augmented with operators signifying temporal concepts, such as always, eventually, and until. Because of its ability to specify temporally complex behavior in terms of relatively human understandable concepts like these, LTL makes fruitful ground for constructing explanations. In our ShopWorld example, we'll give the agent two specifications, one requiring the agent to leave the store while holding the watch, or eventually left store and holding, and one forbidding the agent from shoplifting, never leave the store while holding an object that has not been bought, or always not left store and holding and not bought. We can give to each objective phi I a priority zi, a non-negative integer, and a weight wi, a non-negative real number. Violations of objectives with the same priority can be traded off, using their weights as an exchange rate. Violations of objectives with different priorities can't be traded off. The agent will prefer to satisfy the higher priority objective, no matter how many lower priority objectives it must violate to do so. This is implemented using lexicographic ordering on vectors. The vectors of priorities and weights induce a binary relation over vectors in Rn. In the ShopWorld example, we will give the anti-shoplifting specification a higher priority than the obtaining the watch specification. We can specify a multi-objective LTL planning problem as a tuple consisting of a Markov decision process, a set of syntactically safe or co-safe LTL objectives, a weight vector, and a priority vector. Because we use safe and co-safe LTL specifications, from each such specification phi, we can construct a finite state machine which accepts only on those trajectories tau which constitute good prefixes if phi is co-safe, or bad prefixes if phi is safe of phi. A good prefix is a finite trajectory tau such that any infinite extension of tau satisfies phi. In ShopWorld, for example, any finite trajectory where left store and holding are true at some time step constitutes a good prefix for the rule leave the store while holding the watch. We can use these finite state machines to construct a product MDP whose state space is the product of the original MDP's state space, and those are the specification's finite state machines. We define the satisfaction function for an LTL statement phi and finite state machine state q to be equal to 1 if phi is co-safe and q is an accepting state, minus 1 if phi is safe and q is an accepting state, and 0 otherwise. We can use the satisfaction function to define a vector reward function, R capital Phi, on the product MDP, which subtracts the vector of satisfaction functions at the new product state S times prime from that at the previous product state S times. Using this vector reward function and the binary relation induced by the specification's priorities and weights, P can be framed as a typical reward maximization problem amenable to value iteration. In the ShopWorld domain, because the agent cannot afford to buy the watch and the anti-shoplifting specification is of highest priority, the agent will immediately leave the shop, terminating the episode. Assuming that we have a trajectory produced by an LTL planning agent, we would like to be able to answer queries of the form why psi, where psi is an arbitrary, safe, or co-safe LTL statement. We'll interpret this statement as asking, why did the agent act so as to make psi hold? For example, in ShopWorld, we can express questions such as, why didn't the agent leave the store, why did the agent never buy the watch, and why didn't the agent leave the store while holding the watch? We'll define the minimal evidence that a trajectory tau is unsatisfactory for an LTL statement phi as the minimal set of time-step literal pairs such that for each time-step t and literal L in the evidence, L holds at time-step t in trajectory tau, and each other trajectory that has this set of literals hold at their corresponding time steps is also unsatisfactory for phi, in that it's not a good prefix if phi is co-safe or it's a bad prefix if phi is safe. For example, in ShopWorld, since the agent's trajectory consists of the initial state and one state after it's left the store, to show that the agent never left the store while holding the watch, it is sufficient to know that the agent was holding the watch in neither state. Using this notion of minimal evidence, the agent will respond to such Y queries with an explanation structure, which is a tuple gamma, E, tau prime, and E prime, where gamma is the type of the explanation structure, tau prime is an alternate trajectory, or nothing, and E contains evidence that tau violated one or more LTL statements, with E prime the same as E but for tau prime. Here's how we produce explanation structures in response to the question why psi for an LTL planning agent which behaved according to trajectory tau. First, we ask if tau entails psi. If not, then we return the query false explanation structure, along with evidence that tau did not satisfy psi. This is responding to why was psi true with psi was not in fact true. In ShopWorld, the question, why didn't you leave the store, elicits such a response since the agent did in fact leave the store. Next, we ask if it was possible to behave in such a way as to make psi false. If not, return the neg query impossible structure, which is in effect responding by saying psi is true because it was impossible for psi to be false. In ShopWorld, the question, why didn't you buy anything, elicits such a response because the agent could not afford to buy anything. Otherwise, we compute an alternate trajectory tau that maximally satisfies the agent's specifications subject to the constraint that psi must be false on tau. To do this, we construct a new LTL planning problem augmented with not psi as a new specification with priority greater than all other specifications. We return an explanation structure which shows which specifications were violated by tau and tau prime respectively, along with evidence supporting each such violation. In effect, this allows the agent to respond to why did you make psi true with because making psi false would require me to violate more important specifications than those I actually violated. Here's an example in ShopWorld. Suppose we ask our agent, why didn't you leave the store while holding the watch? First, the agent confirms that it did not in fact leave the store while holding the watch. Second, the agent confirms that it was possible for it to leave the store while holding the watch. Finally, the agent constructs an alternate trajectory in which it left the store while holding the watch, while minimally violating its other specifications. Because the only way to leave the store while holding the watch would be to shoplift, this creates the alternate trajectory of picking up the watch and leaving the store. The generated explanation structure shows that while the agent's real trajectory violated the specification demanding that the agent leave with the watch, the alternate trajectory would have resulted in the agent shoplifting, which violates a higher priority specification. To show how these explanation structures can be useful, we integrated this functionality into a natural language pipeline in Diarc, a robotic architecture. Specifications and queries were represented in an object-oriented syntactic extension to LTL, which allows quantification over objects. Human utterances were parsed by a combinatory categorical grammar parser into queries in this LTL extension, from which explanation structures were generated, and these were passed into a natural language generation module to produce English responses. Here's an example of the natural language capabilities in a version of ShopWorld with two objects, a pair of glasses and a watch. The agent can afford one but not both of the objects, and so it buys the glasses but leaves without the watch. Asking, why didn't you buy anything, yields the response, I bought the glasses. Asking, why didn't you buy everything, yields the response, it was impossible for me to buy everything. Asking, why didn't you leave the store while holding everything, results in the agent generating an alternate trajectory in which it buys the watch and steals the glasses. The resulting explanation structure is held in memory so that the agent can explain both the content of the alternate trajectory and how it constitutes a worse violation of the agent's specifications. In future work, we plan to incorporate explicit causal models so that, in case it was impossible to make psi false, the agent can provide more detail about why this is the case. We aim to tailor explanations to the knowledge of the human interactant, perhaps using some form of epistemic planning. We aim to adapt the algorithm to stochastic environments in which the agent must consider multiple alternate trajectories and their probabilities. We aim to improve the efficiency of the planner since the product MDP approach runs in time exponential in the number of specifications and is thus impractical for non-trivial domains. And we aim to drop the assumption that the agent has perfect knowledge of the environment's transition dynamics. Thanks to our funding sources and to my collaborators on this paper and the LTL project more broadly, and thank you for your attention.